Do you have the... Okay.
Yeah. So I'm very thankful that Benoit agreed to give this talk today here about Birkhoff normal forms for Hamiltonian PDEs. I must say I've looked at his paper with the same title so many times and read so many things and learned many things from it. So I hope we will all be benefiting from this talk about normal forms, Birkhoff normal forms for Hamiltonian PDEs. Benoit, pleasure to
Okay.
have you. Can you please start?
Well, thank you very much for this presentation, and thank you very much for the invitation, actually. So I am effectively going to talk about Birkhoff normal form for Hamiltonian PDs, and that the novelty is that I will do that in the energy space. So this collaboration with Joachim Bernier, who is here, actually, well, in the seminar. And okay, so let's begin with in some sense, an abstract of the talk. And so we want to study the long-time behavior of a small solution of semi-linear dispersive Hamiltonian PDEs on confined domain. So actually all the words are important. I mean, long-time behavior, of course, small solution, semi-linear, we are not able to consider quasi-linear, dispersive, of course, Hamiltonian structure, and confined domain. So typically, well, maybe the most emblematic equation we can consider in this context is the Klein-Gordon equation on the segment 0 pi with Dirichlet or periodic boundary condition, and also the nonlinear Schrödinger equation in 1D or 2D in that case, again with Dirichlet or periodic boundary condition. And what I am going to present today are stability results. So I'm only interested in stability results in the energy space, which is the novelty. So before going on this result, oops, I have a problem. Okay, I would like to say something about the context. So the context, again, is a nonlinear dispersive PDs, but in confined domain. So as you very well know, there is a competition between dispersion, so the wave move away from each other, but also confinedness, so they frequently meet. So these two effects are in competition, and what we could expect is something turbulent or chaotic, turbulent or chaotic dynamics. And for instance, which is the problem with very popular in the recent decade is the problem of the Sobolev norm, which grow with time. So typically, this is possible when the energy migrate from low Fourier modes to high Fourier modes. And well, Fourier modes, that it's in the case of the periodic case, but anyway, let's consider this case. And then the norm, the Sobolev norm HS, in HS, the norm U index S is defined as usual by this formula, where UK is the Fourier coefficient of U. And so we see that if we have a migration from K small to K large, then the norm index S is growing when S is bigger than 1, strictly bigger than 1. So there is a turbulent effect, and you can also expect some more complicated chaotic effect or anything nonlinear effect, let's say. But it turns out that most of the solution of these dispersive PDs in confined domains, for most of the solution, we do not observe significant growth. So typically what we observe is that the Sobolev norm of index S, NES, is almost conserved for a very long time. And actually, for many models, we are no significant exchange of energy, which means that all the modes, the modulus of the UK is almost invariant during very long time. So this long time stability result, and this is what we observe numerically and what is also observed physically in some context. So actually the typical result we can prove, well, the first result maybe in that direction was the result by Dario Bambuzzi, and then it was a result for the wave equation, for the Klein-Gordon equation, and then Dario and I, we generalize in a more general context, and this is the result I want to give you just now as an introduction. So this not a very precise result. It's maybe something like a flavor of the result. So what is the result? The result say that if you take non-resonant, of course, non-resonant is important. I will define the concept of resonances later. If you have also semi-linear Hamiltonian PDEs and you assume something on the nonlinearity, which is a tame property. I am not going to define this property, but essentially it's satisfied in a lot of cases, let's say. Then the results say that for all R, there exists S0 of R, and, such that if you take S bigger than S0 of R, and if you consider an initial datum U0, which is small in the HS norm for S bigger than S0, so small means smaller than some epsilon 0, then for long time, and long time means T smaller than epsilon to the minus R, where R is chosen arbitrarily at the beginning, then you have the norm of U HS is still controlled by 2 epsilon, so it's not growing, and each modes are almost invariant. So this is the result of stability we obtained some years ago, actually. And here P, the coefficient P is related to the degree of the nonlinearity, essentially the degree of the nonlinearity in the Hamiltonian, or P minus 1 is the degree of the nonlinearity in the equation. Okay, so what I want to well, maybe, of course, this I like this result, but the problem is in red. I mean, the problem is that S is large. S is not has to be bigger than S0 of R, and S0 is actually very, very large and depends on R. So in the paper with Dario, what we had is S0 of R of order R squared. And actually, in some recent paper by Biasco, Mazzetti, and Procesi, they obtained S0 of order R. So, but anyway, when you want a very long time, you want R very large. So you have to impose a very high regularity on your solution. So nevertheless, the numerical simulation suggests that stability does not require smoothness, and these you can find this fact in a paper by Cohen, Error, Lubitsch, and essentially they prove that they show that numerically you see stability even in the energy space. So that's why we want to consider this kind of reason, Birkhoff normal form, but in energy space. Good. So before going on this new result, I would like to say something about a recent result in Birkhoff normal form theory. So, of course, there is some pioneering work by Bourgain. I will say, as usual, there is some pioneering work. by Bourgain. And then after the paper with Dario, there is a lot of result about almost global well-posedness. What is almost global well-posedness? Let's go back on this result. Is the fact that sometimes you consider Hamiltonian PDEs that for which you are not able to prove directly a global well-posedness, and this kind of result say that for very long time you have actually well-posedness. So that's the idea of global well-posedness in this context. So actually with Dario Bambuzzi, Jean-Marc Delors and Jeremy Sheftel, we proved this kind of result for Klein-Gordon on Zoll manifold. Then also for quantum harmonic oscillator, this was with Rafi Kimekras and Eric Paturel. More recently, there is a Birkhoff normal form result for water waves. So in a very complicated setting, let's say it's much more complicated, the water waves than NLS or wave. And then there is also a recent result by Roberto Feola and Felice Iandoli where they prove some Birkhoff normal form techniques for quasi-linear PDEs, very new. And there is extension in the Gevrey class and with some Nekoroshev type result by Biasco, Massetti, and Procesi. And I would like also to talk 2 minutes, well, 1 minute about the recent result we obtained again with Joachim Bernier, but also with Erwan Faou, which is a result about rational normal form. So which means, let's say, Birkhoff normal form without external parameter. So what does it mean? So again, I go back to the theorem. We have this condition. We have to know that we have non-resonant Hamiltonian PDE. And to have this non-resonancy, typically you have to modulate some parameter and some external parameter. It can be a mass, it can be a potential, a linear potential, but you have some external potential. So this makes that the result is not exactly the one you would like. I mean, you have a family of equation, and you say that for most of the realization in this family, you have a stability result. So with Joachim and Erwan, we wanted to use internal parameter in the sense that what we use to modulate the frequencies is the initial datum. So moving the initial datum of the problem, you move in some sense the non-linear frequencies, and then you can expect some non-resonance. And the flavor, again, of the results is very, very heuristic, but while no time to really give you a precise statement, is that almost surely with respect to the initial datum, we have a stability. Okay, so now I go back to the result I want really to present today. I mean,
can I ask a question before?
Yeah.
So the main theorem, so non-resonant is non-resonant at all orders, presumably. That non-resonant you can, yeah. And tame means what?
Well, tame, actually, I'm not going to talk about these results. These, let's say, the whole result on the Birkhoff normal form, and the tame property is something like, well, typically, if you have a polynomial nonlinearity, it's okay. If you have in some sense regular nonlinearity, you have no problem, but you need something on the nonlinearity where in such a way you can control this nonlinearity with the HS norm. It's
I see. So polynomial, I should think of polynomial as being okay.
Yeah, of course.
Okay, thanks.
Okay, so actually now I will give the context, the setting for the result in the energy space. So let's consider an abstract setting where we have an Hamiltonian equation. So this is an Hamiltonian equation. The matrix or the matrix G is some Poisson structure. So you have an Hamiltonian structure, if you prefer, for your equation. And you have an initial datum in space E, and E will be the energy space. And what we want to know about this space E is that is an Hilbert space, and you have an Hilbert basis Ek. K is in some set n index D. So this set is a subset of ZD. D typically is the dimension of the PDE. So we will essentially have D equal 1 and n index D equal Z. But in general, you can consider this case. And so you have a decomposition of your solution in modes. So Ek are the modes of your equation, and Uk are the coefficient associated to these modes, to this decomposition. So with this decomposition, you have also an equivalence of, you can see your Hilbert space as a set of sequences, so of the sequences UK. And what you want is that E is equivalent to some discrete Sobolev space, which is as usual defined as follows. So the sum of k to the power 2s UK square is smaller than infinity. So this is typically the discrete Sobolev set. And we want E to be equivalent to some HS for S positive. Actually, for NLS, S will be 1 because the energy space is H1, maybe with Dirichlet or with periodic boundary condition. Okay, so then the Hamiltonian H decompose in a quadratic part, Z2. And so Z2 is the sum of omega k UK square. So omega k are the frequencies, and they are essentially the eigenvalues of the linear part of the equation. And P is the perturbation in some sense, so the non-linear part of the problem. So we have the frequencies, omega k, and then we have a function P, an Hamiltonian P, which is at least C1, but we ask more. We ask P to be regular Hamiltonian in the sense that the gradient has to map E into E. Well, actually, there is some generalization, but let's say that gradient P maps E into E. This is a natural hypothesis to consider this kind of equation. Okay, we want gradient P to be again in the energy space. Then we assume that the nonlinearity is of order P minus 1, which means that at the origin P, the Hamiltonian is of order P. And maybe the most important, the most restrictive hypothesis is that the Hamiltonian is controlled by the energy norm, but also controls the energy norm. So we have these estimates, and is related to the global responsiveness of the equation in the energy space. Okay, so now I have to go to the most important, the most important, let's say, assumption which concern the omega, the frequencies, and we have to assume that these frequencies are non-resonant. And this is a new concept of non-resonant frequencies, and so I want to describe slowly this definition. So we say that omega is strongly non-resonant when, for all R, there exist coefficient, gamma r and alpha r, such that for r star smaller than r, we have the following. So we take a linear combination of frequencies of mode n1, n2, and nr star. So we have nr star different modes, and we take a linear combination of these frequencies, and we want to control this expression with respect to n1. So who is n1? n1 is the smallest index involved in these linear combinations. So we want to control this linear combination with respect to the smallest index involved in the linear combination. What I have also to say, of course, is that the linear combination is with integer coefficient, and we assume that these integer coefficients are not zero. I mean, we are effectively n1, the frequency S1, n1 is part of the combination, and all the other one also. Okay, so it's the coefficient L are not zero. So the point, the abstract of this definition is that we have a control of the small divisor. This is typically what we call a small divisor, using the smallest index. The difference with the result by Dario and myself is that in that case, the control was with the third largest index. So it was related actually to the tame property, well, in some sense. But you see that, of course, if you have a control with respect to the third largest, so you have a control with respect, excuse me, if you have a control with respect to the smallest, of course, you have a control with respect to the third largest index. So this new condition is stronger. But surprisingly, this new stronger condition is often satisfied. This is something we will see at the end of the talk. So I would like to have 2 minutes to show you this, because I think it's interesting. Okay, so then we have the result, and the result is the following one. This is the abstract result, which say and it says the following. So you take R, the order bigger than the nonlinear, the degree of the nonlinearity. Then you have a beta R. We will come back on this coefficient later, and an epsilon 0, such that when the norm of the initial datum in the energy norm, in the energy space, excuse me, is smaller than this epsilon 0, then the Cauchy problem first admits a unique global solution in the energy space. So we are working only in the energy space. And if you assume that T is smaller than epsilon minus R, so for a very long time, you have a control of the energy in each mode. So you have a control of UN square in modulus for time smaller than epsilon minus R. So these quantities are almost constant in the sense that they are controlled by this expression. Okay, so it's very similar to the general result with Dario, but two main differences is we are working in the energy space, but also we have this beta R. So just let's go to this point actually. Because of this beta R, what you can see is that essentially this result makes sense for only finite number of modes, depending on epsilon. And essentially, we could say that the results say that we essentially control a finite number of modes. So another way to say that is that if you fix R and if you fix the number of modes, so this capital N, then for T, you have a size epsilon such that epsilon 0, such that if T is smaller than epsilon minus R and N is smaller than capital N, then you have control of the corresponding energy, UN square. And actually,
nevertheless, Benoit, you have unique global solution in energy space. I mean, I mean, do you control the norm in energy space, or?
Yes, also yes, because actually we have this assumption in here that the Hamiltonian control the energy. So the Hamiltonian is constant, so the energy is not conserved but controlled. Okay. So okay. Just a remark about the fact that we can also consider partially resonant cases. This is not really more complicated for the proof, but it's more complicated for the statement. So I don't want to talk about this today, but you can manage some resonances in some sense.
And so what is the role played by P here? Can I take always P equals R, for example?
P in here, this P? Yeah. P is the order of the nonlinearity.
Ah, okay.
So if you don't take R bigger than P, you obtain the typical local existence result in some sense.
Okay. So it's not.
So it makes sense when R is bigger than P.
Okay, thanks.
Yes, good. Okay, so yes, now I would like to consider concrete examples, because this was a general setting, but to be sure that we have effectively some concrete example, I give you some concrete example. The first one, and maybe the easiest one to consider, is the Klein-Gordon in 1D with Dirichlet boundary conditions. So you recognize the Klein-Gordon, so the second derivative in time equal the second derivative in x. Here you have a mass m, and then you have a nonlinear term, which is of the form g and phi to the p minus 1, so it's of order p minus 1. Okay, we could actually consider more general nonlinearity, but this one is sufficient to understand the result, I think. So then we assume that we have a Dirichlet boundary condition, as I said, and we have initial datum, which consists in giving the function at time t equals 0 and the derivative with respect to time at t equals 0, because we are with a second order equation. So we assume J to be in H1, so it's finite regularity, and we assume P to be greater than 3, just to be sure that this is a nonlinear term, okay, because this P minus 1 is bigger than 2. Then we define this energy in the mode N. This is typical for a wave equation where you have to be to consider a mix where there is two scaling, square root of n square here and 1 over square root of n square. And this is related to phi, and this is related to the derivative of phi essentially. Well, this is standard for wave for Klein-Gordon equation to define the energy in mode n as this formula, and it plays exactly the same role than un square in here. I mean, this is the counterpart of un square in the case of Klein-Gordon. And the results say that for almost all m, almost all mass, so I will go back on this, we have exactly the same statement as in theorem 1, which means that if the initial datum is in the energy norm sufficiently small, depending on m actually, then the Cauchy problem admits a global solution, and you have an almost invariant result about the energy in each mode n, with the same estimate in here with n to the beta. So it's exactly the same, not nothing new. Maybe I want to comment about almost all m, why we have to consider some spatial mass in some sense, while we are not able to consider all the masses. The point is that the frequencies for Klein-Gordon are given by this formula. So omega n is just the square root of n squared plus m, and n is an integer. So to be sure that these frequencies satisfy the non-resonant condition, we use the parameter m. So at the end, we obtain a result for almost all m. And I would like also to compare with the result of Dario in 2003. And the point is that in the result of Dario, you have to consider very regular solution, so HS with S very large. So actually, you have to consider equation where the nonlinearity is C infinity. I mean, the coefficient of the nonlinearity is C infinity. But in here, the function G can be in H1. I recall that G was in front of the nonlinear term. Okay, so we have more equations in some sense, more possibility of equation. The second point, which is in some sense tricky in the sense that typically the paper don't talk about this problem, but we say that we are considering a Dirichlet boundary condition, but if you are considering very large, very high regularity, then in fact the condition, the Dirichlet condition you have to consider is not the Dirichlet condition, but the generalized Dirichlet condition, which means that all the derivative of phi of order 2k for k in an integer, so all the even derivative of phi are 0 at time at x equals 0 and x equal pi. So in here, we have not to consider this generalized Dirichlet condition, but only the normal, let's say, Dirichlet condition. And as a consequence, when you have to impose generalized Dirichlet condition, you see that you need some symmetry in this term. And typically, you have to impose that P is even. And in here is not necessary. So for instance, we can consider the quadratic Klein-Gordon equation when Dario was not able to consider the quadratic case, but the cubic one. Well, okay, so that's the point about the differences, let's say, with the previous result. And now let us consider the NLS case. So nonlinear Schrödinger equation, again in 1D, and again with Dirichlet boundary condition. So you know very well the NLS equation, and you see that I put a standard nonlinear term in here with a coefficient G. Again, Dirichlet boundary condition and initial datum. The initial datum is assumed to be in the energy space, which is in that case H10. We have to assume for technical reason G in H2, but we could expect that H1 is sufficient, but or actually maybe less than H1. And V a priori has to be at least in a bounded potential. So the frequencies for this problem are the frequencies of the linear parts of this Sturm-Liouville operator. And so it's the Dirichlet spectrum of the Sturm-Liouville operator and second derivative with respect to x with a minus sign plus V. So this is a very well studied this spectrum, and we know that this sequence lambda n of V for n bigger than 1, and you have this asymptotic of the lambda n squared plus O1. So now the problem is how we can choose V in such a way the Dirichlet spectrum is strongly non-resonant in the sense of the definition I gave you some minutes ago. And what we choose is the following form of V. So we decompose V in sinus and cosinus. with some scaling n to the minus s and some coefficient Vn. Okay, S is assumed to be bigger than 3/2, essentially to be sure that V is in H1. And Vn, well, we can choose a lot of way to define Vn, but it seems to us that this one is good, is maybe the most natural one, which is to choose Vn as independent real centered Gaussian variable of variance 1. So this Gaussian law allows Vn to be very large if you want, but with a very bad probability, and it's maybe better than the standard way to define V, where we choose Vn in a segment and with a uniform law. But then you have it's not very natural, let's say, to put Vn in a segment. So we prefer in here the Gaussian law. And the proposition is simple. It's the following: there exists a rho strictly positive, so that almost surely, with respect to this Vn, provided that the norm of V is strictly less than rho in H1, then you have the Dirichlet spectrum, which is strongly non-resonant. So when you have this result, you have the theorem 1 as a consequence. So you have this result of stability. And I don't want to state again the theorem 1 in this setting. What I want to give you is a corollary, and a corollary which is another way to understand the result. And is the following one: is an orbital stability result. So the corollary 3 say that if you take V such that the Dirichlet spectrum is strongly non-resonant, so for instance, take V as in the previous proposition, then for all R bigger than 1 and the novelty is S strictly bigger than 1, there exists a constant K and delta such that when you assume U not only in the energy space but also in Hs of 0 pi, then if you assume also that the norm in this Hs is small, then the global solution of NLS satisfies the following. So for T smaller than epsilon minus R, so again for a very long time, you have the leading term of the dynamics, which is given by this formula. So you see that, well, what we have to detail a little bit this formula. Fn are the eigenfunctions associated to the modes, the Dirichlet modes. And so in particular, UN0 is the coefficient in these basis, in this Hilbert basis of the initial datum U0. So we have Fn, we have UN0, and what is theta n? Well, is some angle. I have no formula for you for these angles, but we can prove, we just are interested in the fact that they exist. And so you have a modulation of the modes, the initial modes with this exponential E theta n of t. So this is typically an orbital stability result. And you see that what we obtain is an estimate where we have a delta there. So of course, what we win with respect, U is of order epsilon, and we have an estimate when 1 plus delta. So we need some delta strictly positive. And as you can imagine, delta is related to S. I mean, actually to S minus 1. Okay, so the flavor, the idea of this result is that by asking for a little more regularity on the initial datum, we have the linear term of the dynamics. Okay, so we are no more in the energy space, but almost, because this is true for S just strictly bigger than 1, not very large. So now 2 words about the periodic case, which is more complicated. So just I want to explain why it is more complicated, the periodic case. So for instance, Thomas, you know very well the fact that the spectrum of the period in the periodic case is a bit more complicated than in the Dirichlet case. So we still have a sequence of lambda n in for n now in Z, so n and minus n, but you still have these asymptotic. But you see that then lambda n and lambda minus n are of the same order, n minus n squared. And actually, it's worse in the sense that when you impose some regularity on the potential, then you have this decreasing property on the difference between lambda n and lambda minus n. This lambda n minus lambda n minus n is essentially the gaps of in the spectrum, the periodic spectrum, and you know that these gaps is a decreasing sequence and decrease depending on the regularity of V. So when you assume that V is very regular, then you have a very fast decreasing sequence, and you cannot apply, you have no non-resonance condition essentially. So you cannot apply the standard Birkhoff normal form techniques. But in here, because we are working only in finite regularity, which is actually H1, we can consider, we can apply the result to the periodic case, and considering this kind of potential, again with random, well, Gaussian law on Vn, we obtain the same result for the periodic boundary condition than the result for the Dirichlet boundary condition. Actually, is not exactly true, because I don't want to detail, but essentially we have to fix from the beginning the number of modes you want to control. So it's a bit different. There is a difficulty there, a technical difficulty related to the periodic boundary condition, but we are able to consider this case something which was not possible in the standard method. Okay. I see that the time is well, it's not, I still have a little bit time. Okay, so yeah,
don't worry.
Okay, so two words about the case of in 2D. So of course, 2D is more difficult than 1D. We can expect that, and so NLS in 2D. We consider only the cubic NLS. So why only the cubic? Essentially because we need a global well-posedness result. So we have to consider cubic, and also the spectral problem is much more complicated in 2D than in 1D. So instead of considering a potential, a multiplicative potential, we consider a convolution potential. So it's not the same equation. I mean, it's not the same degree of generalization of NLS, but we have at least the cubic with a cubic NLS equation with a convolution potential in here. Okay, so the energy space is H1. Again, it's not the same as in 1D. And if we assume that the frequency, so the eigenvalue of these operator are strongly non-resonant, we have the consequences of the theorem 1. So the frequencies of these operator is just n squared plus the coefficient, the Fourier coefficient of V. So it's quite evident, easy to describe. And if this sequence is non-resonant, then we have the standard, let's say, conclusion, the fact that when the initial condition is sufficiently small in the H1, then for T smaller than epsilon minus R, you have a control of UN square minus UN UN square times T minus UN square times 0. The little difference, which is again a technical problem, is that you see that we are considering the cubic case. So normally P is 4. So normally in here we have epsilon to 4, and in this theorem we have epsilon 4 minus delta. So we lose something. This delta is in here. We lose something between 0 and 1/2. And why this? This is a technical reason, which is related to the fact that H1 is no more an algebra in 2 dimensions. So you have to pay something, and you pay some part of epsilon to the 4, actually. And the proposition after this theorem is the fact that for typical potential V, effectively these frequencies are strongly non-resonant. So this is quite standard in the case of convolution potential. So it's not new, but it's true, and it's useful for us. Okay, so these are all the examples I wanted to give you, and let me spend some minutes to convince you that the proof is actually very simple. The key of the proof is quite simple. And so the idea, which is a general idea in a lot of work on this kind of PDEs, is to separate the dynamics of low modes from the dynamics of high modes. So let's try to do that. And so you recall that the Hamiltonian is composed by a quadratic part and then a nonlinear part. And P, let's say, is of order P, is exactly something of order P. And so when you want to write a polynomial of order P in the Fourier coefficient, let's say, for instance, you obtain an expression of this kind with some coefficient P sigma n, and then all the modes UN1 to UNP appears. Depending on sigma 1, sigma p can be UN or UN bar. This is typical. Typically, you can think in NLS equation. So you obtain something of this kind, let's say, for a general homogeneous polynomial of order P. Okay, so what is the idea of Birkhoff normal form is to eliminate most of the term of the nonlinear part, because the nonlinear part is the problem. So of course you cannot eliminate all the polynomial P, but you want to eliminate most of the monomials in this sum. So if you want to eliminate this monomial, so involving the modes N1 to NP, then you have to control the small divisor, the corresponding small divisor. This is a standard Birkhoff normal form result, let's say. So if you are able to control this expression, if this is not 0 essentially, then you can kill this monomial. But in our assumption, we have a control of this expression, and this is the control we have. We know that this linear combination of modes, of frequencies, excuse me, is controlled by the smallest index. So the definition here is a little bit complicated, but it's just the smallest effective index in some sense. which means that you take the minimum of the index, but you don't want an index for which you have the repetition ng equal nk and sigma k equal minus sigma j. So this would signify that you don't really have n1 in the equation, in the combination. So the sense, this is not the smallest index, but the smallest effective index. So the standard Birkhoff normal form techniques would come from the finite dimension setting. Actually, is that if you pay this price, I mean the n to the beta p when n is the size of the smallest index, the smallest effective index. So if you can pay this price, then you can eliminate the corresponding monomial. Okay, so if you want to eliminate all the monomial of P such that the smallest effective index is smaller than n, you just have to pay this price. I mean, in the new Hamiltonian you have constructed. So you can then iterate this procedure, and let's say that very roughly, you will obtain a symplectic transformation tau, such that in the new variable, so h composed with tau, is again the quadratic part, and then you have two terms, QR and RR. The second term is really a remainder term in the sense that it's something where we have killed all the term up to order R. So you have something beginning with the order R, so the gradient is controlled by u to the r minus 1. So this is small in the sense that u is small. So if r minus 1 is large, this is very, very small. Of course, you have to pay a counterpart which is related to the capital N, which is the truncation with respect to the smallest index. So this is not a problem. And the other one is correspond to the monomials we were not able to kill in the previous procedure. That means monomial for which the minimal index, the smallest index, was bigger than n. Okay, so because we have only monomial for which the smallest index is bigger than n, you see that the Poisson bracket with un square with n smaller than n will be 0. There is no contribution on the dynamics of low modes coming from this QR. So it's not important, this QR, for low modes. It's just important for high modes. So you have a separation of low modes dynamics. Then the dynamical consequences is quite standard. You take this change of variable and you take the derivative with respect to t of these new variables Vn, and because of this statement of this factor, the only contribution comes from the remainder R, but this is small in the sense of this relation. And you obtain that the derivative of Vn squared, this derivative, is actually of order epsilon r, which means that you are not moving essentially. Okay, so this is the idea, and the point is really that because we can make a truncation with respect to the smallest index involved in the monomials, we can separate the dynamics of the low modes, which was not possible in the previous construction of Birkhoff normal form. So I think, do I have 3 minutes, let's say, or something like that?
Sure, no problem.
Yeah. Yes. Okay, so so I can say something about. So the previous slide was about the key ingredient on the normal form techniques, but now this is about the key assumption. The key assumption is the strong non-resonant condition, which is different from the one used in the paper with Dario 15 more or less years ago. So I put in this definition both the strong non-resonant definition and the weak non-resonant condition. So what is the difference? The difference is that for the strong non-resonant condition, I have a control with respect to the smallest index. So N1 is the smallest one. And in the weak non-resonant condition, I have a control with respect to the largest index. So in that case, I assume that we have ordered the indices. So N1 is the smallest and R star is the largest. So the strong condition control with respect to the smallest index, the weak condition control with respect to the largest index. Okay, and the standard affirmation is that, of course, if you have strong condition, you have weak condition. It is quite evident. And it turns out that weak condition is satisfied for most choices of external parameter. This is already known. And typically for Klein-Gordon, the external parameter was the mass. For KdV, the external parameter was the potential V. So the weak non-resonant condition is true. And the point is that if you assume furthermore that omega accumulates polynomially, fast on the integer, then the weak condition implies the strongest one. And this was a remark by Joachim actually 6 months ago or something like that. And it was very surprising for me because I thought that it was not possible to have such a strong condition. But it turns out that the proof is quite simple. It's very, very simple. And I can give you the proof. And the proof is an induction. So you consider these, I have also to say that I had a K there. A K is just for technical reason again, but this condition without or with K is essentially the same. It's not a big deal to add the possibility of an integer in this linear combination. So anyway, the induction step, you have to go from R star to R star plus 1. So you add one more frequency with modes nr star plus 1 with nr star, which is the biggest one. Okay. So you decompose into your expression and you put in with omega nr star the k star, which is the integer which is close to omega nr star. And then you put a counterpart in here, mk star, but it's not a problem. And you obtain two expressions. The first one by hypothesis, your induction hypothesis is controlled by gamma n1 to the minus alpha r, this is induction. N1 is the smallest of these N1 to nr star. And then the second part, well, you know that this polynomially accumulates on the Z, which means that the difference of in here is controlled by nr star to some power, minus negative power, nr star plus 1, excuse me. And then, well, it's easy. Either this coefficient is controlled by this one. So either you have this condition, and if you have this condition, we are done because this expression is bigger in here, is bigger than gamma divided by 2, n1 to the minus alpha r, and it's good. But if this condition is not true, that means that actually n this nr star plus 1 is smaller than n1 to some power, actually. So it's not so big, actually. And because it's not so big, you can use the weak condition to control the small divisor with respect to the largest index, which is nr star plus 1. But once you have a control with respect to the largest index, because nr star plus 1 is controlled by n1, you have a control with respect to n1. So finally, it's a very simple argument, and you obtain the strong condition. And I will stop there, and thank you very much for your attention.
Thank you, Benoit. Thank you. We have time for a quick question before we. I actually was. You answered the question in the very last slide that was always kicking in the back of my mind. Is the role of the symplectic space versus the energy space, because you seem to control the modes, the difference between the modes and the initial data in the symplectic space, not in the energy space. Like in the NLS, you control it in L2. For the Klein-Gordon, you control it in H1 half.
Yeah.
And is this because of your symplectic transformation, or where does it come in?
I mean, okay, maybe I didn't understand very. So let's say.
So here, for instance, and what you said, theorem 5, you're controlling the difference in L2. I mean the square. So this is basically.
Well, okay. I agree.
And the Klein-Gordon, you control it with H1 half. You get square root of n as opposed to n.
Let's go back, for instance, so for this one, for Klein-Gordon.
Right. You see, you get, it's basically you're controlling the difference in H1 half, which is symplectic, as opposed to the.
Yes, but okay, but you see that, well, we could say it slightly differently, but because of, well, we could say that we can control the sum of this expression, not only each ones. So, and then we can obtain some control in some, not exactly energy norm, but some norm in between L2 and H1. But essentially, this result is only useful when n is not too big because of this term. So we prefer to give the result for each n and not for some norm of that will be effective. I agree with you that is a bit.
Is your beta is beta small? That's what I'm really.
Yes, beta is not small, actually. It's not small at all. Beta R is quite big. It's quite big.
So, okay, so I had misunderstanding.
Yeah. So maybe we can go back to the abstract result. Excuse me, this one. For instance, in the case of the standard case, I mean, with high regularity and so on, what you can have is something like that with n to the minus s or something like that, not n to the beta r. So then you can prove that you deduce that effectively is the HS norm, which is almost conserved.
Right.
But in here, you can only prove, essentially, you have to treat differently the case of the low modes and the high modes. And so the real conclusion is only for the low modes. For the high modes, we have nothing very, very performant, very.
So the way you wrote the Klein-Gordon has nothing to do with this practice, just because it's fine. You could have multiplied everything by n and the power of beta by 1. Yeah. Okay, thanks. Any questions? Okay, Benoit, thank you very much. And
thank you. Thank you too.
Hope we'll see you all soon, and we enjoyed the talk. I think Keishan asked you for putting the talk on the web.
Yeah, it's okay, no problem.
And maybe you can send the slide to her as well. That would be great.
Yeah.
Thank you.
Thank you. Thank you.
Thank you. Thank you.
Bye.
Thank you.
Thank you.
Thank you.
Thank you, Benoit.